All right, today we're going to be in Power Focus Area 6 talking about electric circuits. And we're going to go over some of the basics of that. First off, what is a circuit? So if we're talking about circuits, you've probably at least heard of them, but you might not realize exactly what they are. Fancy definition is any path along with electrons can flow. For us, just think of electrons as electricity. So when we hear electrons, think electricity. Electrons, for us, it'll be basically the same thing. So circuit's any path that lets electricity flow, like we see down here. Here's a path that has a battery. If you follow it out of the battery, it has a light bulb, a switch, some more wires, and back. And this switch just means it could close and open, but we'll talk more about those in a second. So an important thing, electrons, or remember we said electricity, will only flow if the circuit is complete, that has no gaps or spaces between the terminals, the ends of the battery. So in the one we looked at down here, we did have a gap. We said that when the switch was open, there's this opening or a space and the electricity wouldn't go around. Notice this lamp is not on, the light's not on because it's not a complete path. And we'll show you some ones that do have a complete path shortly. So make sure you fill out your notes that go in our checkpoint. And you can always pause here if you're watching because I'll just pause for a second and then move on to the next slide. So we're going to learn about two types of circuits and we'll build these eventually, open circuits and closed circuits. So if you look at the picture here, it's not hard to figure out why they're called open circuits. If we look at the complete path of the circuit, we follow it. There's an opening. Okay, this picture is more like the ones we'll end up making, but if we follow it, there's an opening as well. So an open circuit is any circuit that is broken or has a gap or a space or an opening that doesn't let electrons or electricity flow. How do we know by a picture? There's two ways. One, we just showed you, there's an opening or a space. And two is whatever's connected, like the light bulbs, they won't work because the only way they can work is if electricity can go all the way around the circuit, and it won't happen unless there's no openings. Now notice here, we're talking about a closed circuit. Well, the light bulb is on. The light bulb is on in a closed circuit. There's no openings, so I can just keep going around and around forever if I'm electricity or electrons. Now, we'll learn soon that this is not technically an opening. That's a battery. That's a symbol for a battery. So even though it looks like it, that's not an opening. So this is also closed, and it goes all the way around the electricity, the electrons. And really, we didn't show it yet, but that's the definition of a closed circuit. Complete paths for the flow of electricity or electrons. How do we know? Well, there's no spaces or whatever's connected like the light bulbs do work. That's what we look for in a closed circuit. So make sure you fill out all of this. Compare and contrast open and closed circuits. Remember, both have to have a power source, somewhere to get the electrons or electricity from. Open circuits, there's some kind of space and opening, so the electricity won't go all the way around the circuit and nothing works like the light bulbs. Closed circuit is a nice complete path, and that will let electricity flow and turn on whatever's connected like a light bulb. And then that question down here, it said if a light bulb is in a closed circuit and an open circuit, which one will have light bulbs turn on? Well, slowly we're going to figure out it has to be closed because closed means it's a full path. If you're sitting in your room right now and your lights are off, your light switch can turn them on by closing the circuit. So when you actually flip a light switch on, what it's really doing is closing the circuit, closing that gap, and that's why electricity can then flow and turn on your lights. So the basic parts of circuits, and we're going to build circuits eventually in here, are batteries, switches, and then something on the next slide we'll talk about too. So whenever you think of batteries, you're like, well, that's where the power comes from. And instead of thinking of power, think of electricity. It's electrical energy is what's coming out of it. It comes from the chemicals inside the battery. So what's really happening is we're transforming chemical energy into electrical energy. But the most important thing for us for batteries is that's where the electricity comes from. Electrical energy, we said, is the movement of electrons. Well, here's a fancy word for that, current. So when we say moving electrons or moving electricity, now we have a third word that means the same thing, current. So for us, current, electrons, and electricity all mean the same thing. And it's all created from the battery. All right, switches, just like the light switch in your room, can turn a circuit on or off. Look at the picture. If I open my switch, if the electricity is coming in a wire here, it goes here. We have a space, an opening, the circuit's open, so it won't work. Here, I have the electricity coming in. It can go all the way around, connect with my wires and my battery. A closed switch makes a closed circuit, which is complete and turns on whatever's connected like a light bulb. Another definition is of a basic part of a circuit is resistors. Resistors are the hardest to remember of these. Current we'll eventually remember is just moving electricity, moving electrons. Resistors, though, they control how much current the circuit gets. The reason they control it is they use some of it. So there are things that are made to use some electricity up on purpose to slow down the movement, and those are resistors. But light bulbs are the most common example of resistors that we will talk about. And the main reason is they have to use some of the electricity. They convert the electrical energy into light that you see and heat. Hopefully you don't touch your light bulb, but if you did, you'd feel heat. So there's less current to get back to the battery. So when the battery runs, gives off electricity, goes through the light uses some of it. And if you leave your light on always, eventually it's going to go out because the battery that's connected to it will run out of it. Now, if it's your house, eventually the light bulb will burn out. That's a different thing. So make sure you fill that in your notes. So we're going to make some schematic diagrams. You can't really do it on your own, but we're going to make them in our project. So if you won't be able to make them now, don't worry about it. But you do need to realize these symbols in a schematic diagram are basically a fancy way of saying a circuit picture represent the parts listed here. So a straight line is just a wire. When we see this, it does not mean open circuit. It means it's a battery. And that's one that's super important to remember, because if you don't remember that, you might think it's an open circuit. A resistor, we said light bulbs are resistors. We draw them like this, the squiggly line. Don't worry about capacitor. We're not going to worry about those this year. And then an open switch is just a wire that's open with this little T to show it's a switch. A closed switch is the wire just with the T to show there is a switch, but it's closed. So pause here and try to answer these questions before I give you the answers. W, X, Y, and Z are different parts of a circuit. See if you can remember them from that slide before. All right, Z, it's actually in this picture 2 batteries because we have those 2 spaces there. X is a open switch. Although they didn't draw the T, sometimes they just draw them like this when they're open. And W and Y are actually the same thing, just drawn 2 different ways. We know this is a light bulb, but a light bulb is also an example of what W is, and that's a resistor. So it'll take some practice, but eventually you'll know these symbols and be good with them. There's a short circuit video that hopefully it will work. It's been giving me some issues even in class, but all right, here we go.
Let's begin by looking at how a simple circuit allows a light bulb to light. A circuit is a route through which electrical current can flow. In our example, electrons flow from the negative side of a D-cell battery to a conducting material on the base of the bulb. From there, the electrons flow up a wire that is inside the bulb and across the filament, which is the part of the bulb that actually lights. When the electrons go through the filament, some of the electrical energy is changed to heat and light energy. The electrons continue down another small wire inside the bulb to another conductor on the base of the bulb. The electrons finally make their way to the positive side of the battery. There would not be a complete circuit if the electrons did not travel to the positive side of the battery, and the bulb would not light. When there is an unbroken path on which electrons flow, as in this example, it is called a complete circuit. The unbroken path that the electrons follow is called a closed circuit because electricity will only flow on an unbroken path. The light bulb will not light unless there is a closed circuit. Now look closely at the light bulb and you'll notice that there is a
I'm going to skip that last part because it's not really relevant to what they talked about. The most important thing was they showed you the diagram of a closed circuit, the light bulb working, and also that the electrons or electricity come out of the negative side of the battery. That's something that'll matter a little in our project. Last thing we'll talk about today are something called electrical shorts. An electrical short, sometimes they'll just call it a short, is a direct path from one side of the battery to the other without any resistors. Remember, resistors like light bulbs slow the current down. They help control it. We need to do that. In this picture here, here's my negative side of the battery. Electrons come out and they can get all the way around super quick because there's nothing slowing them down. Well, who cares, right? Well, you should care because electrical shorts are very dangerous because with nothing to slow down the current starts to go super fast, which heats it up, and eventually it can cause sparks or fires even. Luckily, houses are wired in a way that if a short happens, your fuse box just goes off, so there won't be a fire. But anytime your fuse box goes off, like a room just loses power, it's because there was a short and your house is kind of protecting itself with the way it's wired. And here's the last thing we'll talk about is why they called it a short. Yes, now we know shorts are a path that have no resistors. Shorts are dangerous. But actually it makes sense because shorts are shortcuts often. If you look at this picture, there's two paths that the electrons could take. So I can come this way, like the arrows are showing, or I could keep going all the way around through the light bulb in path 2. Well, remember, light bulbs are resistors, and electricity takes the path of least resistance. In other words, it doesn't want to be slowed down. It wants to go as fast as it can. So if it can avoid this light bulb, it will. It'll take the shortcut, which is why we call it a short, and it will only take path 1. Even though the light bulb is in a closed circuit, the light bulb in this situation would never go on. And the reason is the electricity skips it, it takes a short path, and eventually could cause a fire.